Good morning and good afternoon. Thank you for attending the CXL Consortium CXL 4.0 Specification webinar. Today's webinar is presented by Debendra Sharma and Mahesh Natu. I will hand it off to Debendra to begin the webinar.
Thank you, Elsa. Greetings, everybody. It's an honor to present this webinar with Mahesh Natu on behalf of CXL Consortium. Compute Express Link, or CXL for short, it's an open industry standard. The consortium has 280 plus members worldwide. The current set of board members are listed here. Next slide, please. So this is a timeline of the CXL specification. You can read through it, but basically since over the last 6+ years, we have been through multiple revisions of the specification. In each revision of the specification, we have added new features, new usage models, or we have increased the frequency in order to get more bandwidth. And all of these evolutions, and we'll talk more about that in the upcoming slides, but throughout all of this, the key thing to remember is even as we keep adding things, we have evolved the specification in a fully backwards compatible manner. In other words, if you take a design that was done to CXL 3.0, it will still interoperate with a design that was done to CXL 1.1. And that's the promise of backwards compatibility. Next slide, please. Here is the agenda for today. We'll talk about the industry landscape and how CXL fits in there. Then we are going to talk about the past 3 generations of CXL in the context of the different computing challenges that it addressed. Then we'll do the deep dive to CXL 4.0 and finally conclude. Next slide, please. When we look at the industry landscape today, we see some clear mega trends emerge. Cloud computing has become ubiquitous. Networking and edge computing is increasingly using the cloud infrastructure. Of course, AI is there everywhere. There is basically an insatiable demand for compute, memory, and I/O. Heterogeneous processing is mainstream, and we are deploying different types of compute to solve different types of problems. So general purpose CPUs, GPUs, custom ASICs, FPGAs, each of them has a place in this compute continuum, and they are used to solve specific class of problems. Now, in addition to the demand for this heterogeneous computing, what we see is the need for increased memory capacity and memory bandwidth in platforms. For quite a while now, we have been bottlenecked on the memory side in order to deliver the power efficient performance. Next. Now let's talk about the computing challenges with CXL. So CXL is built on PCI Express infrastructure. PCI Express, it works really well for a large class of I/O needs, but there are some emerging applications that require additional protocol semantics for delivering this power efficient performance that we need. PCI Express is fundamentally a non-coherent interface. So new usage models, like I talked about, those that need heterogeneous computing with finer grained data sharing, things like AI use cases, machine learning use cases, some of the smart NICs that people are deploying, they need more than the non-coherency semantics. They need basically the coherency and memory semantics. So let me try to explain that with the diagram here. Now, the picture on the left represents the world with PCI Express, and then the one on the right would be with CXL, where we include the coherency and memory semantics. On the left side, system memory, which is basically DDR today, that's cacheable memory, but only within the context of the CPU hierarchy. So any access from the PCI Express devices, whether it is your GPUs or FPGA or any other purpose-built AI accelerator to that system memory, it happens through memory read and writes. Those are non-coherent on PCI Express. So a PCI Express device, it cannot cache a memory address to exploit either a temporal locality or a spatial locality, or even share data coherently, seamlessly back and forth with other entities. So fundamentally what happens is that the root complex inside the CPU, it enforces the PCI Express's producer-consumer ordering model. And what that translates to is things like PCI writes or atomic operations. They go through a write cache in the root complex inside the CPU. And the reads are dealt as coherent snapshots. And by the same token, if you have memory that is attached to a, PCI Express device, let's say, your HBM inside the GPU, that cannot be accessed coherently by other entities. They're only accessed non-coherently using PCI Express. And again, this non-coherent access on the PCI Express model, it works really well for a large class of streaming IO operations, whether it is networking, traditional networking, storage, even coarse-grained offload accelerators, where you move your entire data structure back and forth between system memory to the accelerator for specific functions, that works well. Now, but for this emerging classes of applications that are being deployed for doing AI and ML, or even for the smart NIC kind of usages, we need finer grained heterogeneous processing where your CPUs, GPUs, FPGAs, purpose-built accelerators, even near memory processing entities, they want to access parts of the data structure, and they want to do that very collaboratively and simultaneously with each other. So that's where moving your entire data structure back and forth suffers the latency as well as bandwidth overhead. So that's basically what CXL did. In order to solve the first challenge, which is around this heterogeneous compute, by introducing coherency and memory semantics on top of PCI Express, in order to perform heterogeneous processing efficiently. So this enables the devices to cache the system memory as well as to cache the memory of other devices in a seamless manner. Next. Now let's talk about the challenge number two. As I said before, memory has been a scalability concern for quite a while. So if you look at the picture on the left, the memory bandwidth per CPU core is going down. And you can extend the same picture for other type of computing entities also. As shown in the middle figure, the cost of the memory for every bit is kind of flattening out. So as we are adding more and more memory into the platform, we are basically increasing the cost of the memory as a total fraction of the system cost. So costs are increasing. Bandwidth is not keeping up. That's the first two pictures there. And what's happening to the demand? The demand is exploding, as you can see on the picture on the right-hand side, which is what you expect to see in this AI ML era. So basically, we have a memory wall here, right? So we can, of course, keep on adding more DDR channels, more memory channels, as we have been doing. But even with that, we are not keeping up, as you can see. And fundamentally, the key reason for this mismatch is the scaling inefficiency that you have inherent with a parallel DDR interface. So even adding more and more DDR channel, it significantly adds to the platform costs and also introduces signal integrity challenges when you are having that many wires that are running around in your board. So in principle, PCI Express pins are a great alternative, and that's what we will show, that how we turn that principle to reality due to because of the superior bandwidth on a per pin basis. So let me give you an example. If you have a by 16 PCI Express 7.0, which basically runs at 128 giga transfers per second, you need 64 signal pins. The raw bandwidth, 512 gigabytes per second. Now, if you take a DDR5, 8,000 mega transfers per second. That's about 200 signal pins, and you get 64 gigabytes per second. So you can see 64 signal pins for 512 gigabytes per second versus 200 signal pins delivering 64 gigabytes per second. It's about a 225x per pin band difference in bandwidth, and that difference is going to keep on increasing as PCI Express keeps doubling its data rate, right, every 2 to 3 years. Now, additionally, with the PCI Express kind of a fun factor, the device is not constrained to be placed next to the CPU. So thermal challenges like, hey, you must be within 15 watts, those restrictions don't exist, or you can relax those restrictions and you can deliver even better memory performance. And CXL solves this problem, this challenge, by offering memory semantics. Most importantly, it is agnostic to the type of the memory technology that is deployed. So you can even deploy cheaper memory there to keep your costs under control. You don't need to have the most expensive type of memory. So this is where our memory semantics helps with addressing the capacity challenges, the cost challenges, the bandwidth challenges, and then the scalability challenges It also provides a pathway for enabling new type of memory technologies like persistent memory along with the traditional DDR. Next slide. So the first two challenges were solved with or addressed with CXL 1.0. So let's talk a little bit about the approach that CXL took. Basically, we have a three-pronged approach, and it's done to ensure the ease of ecosystem adoption along with while delivering the power efficient performance that we need. First, CXL is built on top of PCI Express infrastructure. We totally leverage PCI Express, as you can see on the picture here. Basically, there are three protocols that run on top of PCI Express 5. CXL.io, which is fundamentally PCI Express. It's done for all the IO, traditional IO type of things. CXL.cas is for caching semantics, and CXL.mem for memory semantics. And they get multiplexed and sent out on the PCI Express 5. CXL.io is basically identical to PCI Express, is used for things like device discovery, event reporting, errors, those kind of things, IO virtualization services, direct memory access. And basically with PCI Express infrastructure, what happens is we have lowered the barrier of entry for CXL because PCI Express is so ubiquitous, right? You basically get plug and play. You are using a we are using a PCI Express slot, so you can choose to put in a native PCI Express device, or you can even choose to put in CXL. It's just full plug and play there. Second aspect of CXL is low latency in the context of caching semantics and memory semantics. Caching and memory protocols, they need low latency so that your system performance can be delivered. We are expecting latencies in the range of existing symmetric multiprocessing cache coherency links that we use for in a multi-socket system for delivering for accessing the memory that is in the nearby socket. And the specification guidance in that regard for the latency is, let me give some examples. Pin to pin, if you send a snoop to the device, we expect 50 nanoseconds the response to come back. If we send a read request to a device, a CXL device that is hosting DRAM, the latency expectation is 80 nanoseconds. Now, so that basically works to the NUMA kind of latency, like you want to have similar latency when you access memory in a nearby CPU socket, which is about less than 200 nanoseconds ballpark for the load to use latency if you look at the instruction level. There is also a reporting mechanism. By the way, if you say, hey, I have a new type of memory whose inherent latency is more, but it offers certain characteristics that is very beneficial, there is a reporting mechanism that we provide so that the system software can map that to the appropriate usage in order to not to adversely impact the performance. Third aspect is CXL is an asymmetric protocol. So the protocol flows, message classes, those are different between the host device, host processor and the devices. It's a conscious decision to keep the protocol simple and the implementation easy. Basically, orchestration of the cache coherency protocol, it varies very widely between the different architectures and even within the same architecture between implementations at different points in time. And that's basically what we abstract away. We don't send it out on the CXL link as a result. And everybody has their own way of orchestrating. So effectively, we have abstracted out about 12 commands, which are basically for the messy protocol that CXL devices need to follow, making it really easy for them to deploy it. Next slide. By the way, all of these things, there are detailed webinars on the website that you can go and take a look for each of these revisions of the specifications, as well as there are white papers on our website. CXL, the first generation 1.0, 1.1, it was a direct connect between the host and the device. And as I said, it was targeting the first two challenges, heterogeneous compute and memory scalability. There are three types of usage models. The left picture is a type 1 device, which basically needs only caching semantics, along with, of course, the IO semantics. And those are for things like smart NIC. And there, what happens is that you want to have better performance with things like the partition global address space, PGAS, that ordering model, which is different than PCI Express. So you can deploy the caching semantics to do that PGAS ordering without incurring performance penalty with the traditional loads traditional producer-consumer ordering semantics, or you can do enhanced atomics with using the caching semantics. Of course, you have the the bulk DMA you can move using the CXL.io, which is PCI Express. So deploy the right thing for the right set of problem statements that you are trying to solve. The one in the middle is a type 2 CXL device. So there the typical usage includes GPUs, FPGAs, AI accelerators. Those are for dense computing. Now these devices have some local memory attached to them. Actually, all of them have these days have local memory attached to them, whether it is on package or off package. On package is typically your HBM kind of memory. Now, for doing the computation, because these are very powerful computing entities, and we expect them to implement all three protocols. The caching and memory semantics will be used to populate and pass operands and results back and forth, right, between these different computing entities, between whether it is the accelerator entities, different accelerator entities, or the CPUs. And this can be done with very low latency and high efficiency. The system on the right is basically a type 3, which is a memory expansion device. And this is fundamentally for addressing the second challenge of memory scalability. And the usage would be memory bandwidth expansion, memory capacity expansion, as well as tiering of memory, including storage class memory. These only need to implement CXL.io and CXL.mem semantics. Now, this memory will be mapped to system memory as cacheable memory, and the host processor orchestrates the cache coherency. It relieves the devices from having to implement the complex coherency flows. All it needs to do is just implement memory reads, writes, and it doesn't need to implement the CXL.cache. So these are the three types of devices that we have with CXL 1.0 and 1.1. Again, the left two are for heterogeneous computing challenges. The right one is for the memory scalability challenge. Next. Now let's talk about the third challenge, which is fundamentally stranded resources in a data center, right? Or in any data center, that is. And the best example is memory. Memory is often underutilized in servers. And what are the implications? Of course, the implications are cost and the implications are power. And of course, that doesn't bode well for sustainability goals. Now, system architectures fundamentally are tightly coupled, irrespective of whose system architecture you look at, right? Your compute entities, memory, and IO devices, they belong to one and only one server. Now, as a result, each server needs to be over-provisioned to handle reasonably worst-case workloads. Now, for example, a server that hosts an application, it cannot borrow memory from another underutilized server in the same rack if there is a spike in the memory capacity demand because of some application that is running. Now, if enough memory is not available, then what happens is that you will suffer the performance consequences resulting from page misses. Now, as a result of that, what happens is system vendors, they over-provision memory when they're designing system, and this results in the underutilization because most of the time those over-provisioned memory is not used. And multiple cloud service providers have publicly reported about this resource stranding and having adverse implications on power, cost, performance, sustainability goals. So what we did with CXL 2.0 is that we enabled pooling of resources such as memory or accelerators across multiple servers. You can see that in the picture there. Now, memory pooling at a finer grain can be supported by multi-logical devices that can connect up to 16 hosts or 16 different servers. And each of them is assigned a non-overlapping piece of memory, and those pieces can move. Like, for example, if I have a server that's running and I need an extra terabyte, I can go to this pool and get an extra terabyte of memory. Once I'm done with that, I can release it back so that somebody else can use it. That's the idea here, right? As opposed to everybody putting in an extra terabyte in case somebody needs to use it, right? So you just put things in the pool and then you go and get them from the pool when you need it. When you don't need it, you basically release it back to the pool. It basically follows the hot plug flow, standard hot plug flow. And this capability, it was huge. and it enables resources like accelerators or memory that can be pulled at the rack level, and it's the best use of your resources. It was a huge innovative breakthrough for tightly coupled system. And again, the goal was to make sure that we are the stranded resources problem is basically what we are addressing with that. We can dynamically basically compose systems with additional memory or accelerators that exist from the pool, right? You can go and get it and then move it back whenever you don't need it. So in summary, stranded memory and compute resources at the data center was the challenge number 3. And the disaggregation approach that we have with CXL 2.0, it optimizes that resource utilization while delivering lower total cost of ownership, TCO, as well as power efficiency. Next slide. CXL 3.0, we provided the scalability the scalability challenge, which is the another one of the challenges that we have. Challenge number 4. It's basically how do you do scale up with large distributed systems that rely on fine-grained synchronization. And these are examples are things like large machine learning model that face high costs and low efficiency when you are especially scaling to thousands of nodes, right? And of course, people traditionally do message passing. If you go through a networking stack, there is a higher latency, all of that. And a lot of the research suggests that if you have shared memory implementations, and which is what people are doing, that could significantly improve that, especially for things like machine learning kind of applications. But we don't have a industry standard way of doing coherent shared memories. We didn't have one of doing coherent shared memory system. Now, let's see what we got with CXL 3.0. So first of all, we just doubled the bandwidth on a per pin basis and with zero latency adder, right? So that way, all the usages are going to get double the bandwidth, right? Irrespective of which challenge you're solving. That's a common theme across the board. We also introduced fabric capabilities in order to address this challenge, in order to build larger system. CXL 3.0 scales up to 4096 CXL entities. And what is an entity? Things like your CPU, GPU, Type 3 device, all of those are entities. So you can connect up to 4096. We enable direct peer-to-peer cache coherent access to host managed device memory, HDM, by bypassing the host. So what happens is that if you're connected through switches and you want to access memory, you don't necessarily need to go all the way up to the host and then come back into the device. You can just access the device directly. And since these are coherent accesses, and I just said that, hey, type 3 devices don't participate in cache coherency protocol, the question is, okay, how do you resolve coherency conflict? Well, the way we resolve it is we introduce something called back invalidate. It's just a command on the memory cxl.mem class. And devices always have a directory, so they can just look up a couple of bits in the directory and say that, is this line, can I provide access to this line to somebody, right? That's trying to do a DMA into that particular cache line. If, let's say, the CPU has it, it's just going to ask the CPU to resolve the cache coherency conflict. It's not going to do it by itself. We can do now dynamic composability by binding and unbinding of resources in a much larger scale than what we did with CXL 2.0. And most importantly, we introduced with that back invalidate, we can have shared coherent memory access across multiple servers. Because you have a directory, you can or you can have a Snoop filter on the memory side, and then there are multiple hosts. If they are sharing and you need to recall a line, then you can always send the back invalidate to the appropriate servers and let them resolve their independent cache coherency conflicts and send you a message back on the memory side saying, hey, you can go ahead and from my side things are clean. So the other thing CXL 3.0 did, which we started with 2.0, was we introduced a bunch of security features, but we enhanced it to provide support for confidential compute. So in summary, CXL 3.0 addressed the challenge number 4, fine-grained data sharing and low latency message passing in distributed composable system at the rack and pod level. Next slide. So now let's talk about the CXL 4.0. There are 3 major things in CXL 4.0. that we want to talk about. First is doubling the bandwidth to 128 gig. Remember CXL 1.0, 1.1, and 2.0 were 32 giga transfers per second. We introduced 64 giga transfers per second in CXL 3.0, and now with CXL 4.0, it's 128 giga transfers per second. Of course, let me repeat again, everything is fully backwards compatible. And again, with zero latency adder. Okay. Now, this enables, of course, rapid data movement between CXL devices, and it improves directly the system performance. You just double the bandwidth. We maintained previously we'll see this in the next slide with standard, the same type of fleet arrangements, everything else just running twice the frequency. But given that we doubled the frequency, now we are natively supporting by two devices. And by that, what we mean is, let's say if you have 16 lanes coming out of a CPU, you can connect to a by 16 CXL device. You can connect to 2 by 8s. You can connect to 4 by 4s. Now you can connect to 8 by 2s. And these are for things like SSDs that don't need a lot of bandwidth on a per device basis. Those are aggregated bandwidth, but they need the capability. And also, given the wide usage of CXL, especially people want to move things farther and farther away, and you want to aggregate, you want to do resource disaggregation, we are supporting up to 4 retimers for the increased channel reach, up from 2. You don't need to use them, but if you want that capability, we put in. Second aspect is around CXL bundled port, and this is the ability to aggregate devices, and we'll talk more about that. And last but not the least, given that CXL is being widely deployed for memory, there is a lot of RAS enhancements that as people are deploying that they want to have, and so those got standardized in the 4.0 specification. Next slide. So 4.0, we doubled the bandwidth while keeping the latency the same. We use the PCI Express 7.05 with 128 giga transfers per second. So we use the same forward error correction, FEC, and CRC as PCI 7.0, which was again the same as PCI 6.0. And from a CXL perspective, no changes from CXL 3.0, FEC, CRC. So let me explain that with the picture on the right here. So the top picture is PCI Express 6.0 fleet layout. So you have 236 bytes, that is for transactions, like things like memory read, write, those kind of things. Then you got 6 bytes, that's DLP, that is data link level packets. Things like, ACK, NAC, those kind of things, power management. Then those 200 and 248 bytes are protected by 8 bytes of CRC. And then that entire 250 bytes are protected by a 6 byte of FEC, and that's how you get 256 byte. Now that 6 byte of FEC that you have, it's basically a 3-way interleaved FEC mechanism. So that means there are 3 FEC groups, forward error correction groups. One is 85 bytes, the second one is 85 bytes, and then the third one is 86 bytes. So 85, 85, 86 adds up to 256. In each FEC group, there are 2 bytes for error correction. Okay, so 2 bytes per group, 3 groups, that's how you get 6 bytes of FEC. And again, there is a detailed paper there that you can go look into, which we have listed at the bottom. Now let's look into what did we do for CXL 3.0 and also same way with CXL 4.0. It's a standard 256 byte layout that we have. The 2 byte header, which was fundamentally within the DLP up above, we moved it to the front. And this is basically saying, hey, which type of, is it CXL.io, CXL.cas, CXL.mem? It also has things like what I'm hacking this fleet, I'm knacking this fleet, I'm replaying this fleet, those kind of things, right? Basically, fleet management level things are upfront. Why is it upfront as opposed to being in the same place as PCI Express? Well, PCI Express has only one protocol, PCI Express. Here we can go to CXL.cas, CXL.io, CXL.mem, or even we have something at the link level of management, right? So we want those information up front so that we are not doing a store and forward latency. That's the reason why we have moved it up front. You have the same 8 byte CRC and then the 6 byte FEC as PCI Express after that. Last one over here, the third picture is a latency optimized fleet layout. And you will see that same 2 byte fleet, But you will see that there is and same 6 byte FEC in a different location, but same concept. And but then instead of one 8 byte CRC, we have two 6 byte CRC. Fundamentally, each CRC protects the flit half. So you get the first 128 bytes, the even flit half, that is protected by that first 6 byte CRC. Then you get the next odd half, that is protected by that 6 byte CRC. By the way, FEC is not protected by CRC. FEC protects it all, right? CRC protects the data, and FEC protects the data as well as the CRC and the header also. So the reason we do it in this way is that, when you get the first 128 bytes, you will check the CRC. If the CRC passes, you can consume that, right? You can commit to that 128, the first 128 bytes, whatever data information you got, right? Basically 120 bytes would be interesting. You can commit it. As a result, you didn't have to wait for the 256 bytes. Of course, you're pipelining it, but even somewhere in the pipeline, you're waiting till it did that thing come or not. So you're allowing it to proceed as soon as the CRC passes. And what happens if there is a CRC failure? Maybe there is a bit that has flipped. Well, in that case, you wait for the second half to come by. You apply the FEC across the entire 256 byte within the three FEC groups that we talked about. Then you're going to check for the CRC, individual CRCs. And if things are good, you're going to consume it. If something fails, then you are going to ask for a replay. Okay. Second thing we did is we provided optical enhancements, which came with PCI Express 7.0. So 7.0 introduced, optical links that can interoperate with PCI Express electrical. So that comes to us based on that. And then we talked about 4 retimers. And we talked about all of the standard flit stuff. So I'm going to skip that. There are some numbers given in terms of fit, which is failure in time. We measure things in failure in time, and we have very low fit here. 0.026 is pretty low. Okay. Any silicon generally has at least 2 or 3 orders of magnitude of fit. So 0.06 in a link, 0.026 in a link is practically zero. We talked about native by 2 support, and of course, these extend to the lower data rate, 8 gig, 16 gig, 32 gig, 64 gig, and of course, all the prior generations of CXL still works. Now, let's go to the next slide, and at this point, I would like to hand it over to my colleague, Mahesh Natu. Mahesh, take it away.
Thank you, Debendra. So let's pick up from the second major improvement that was done in CXL 4.0. So let me first kind of state the problem that we're trying to solve. So obviously, you can all see that the bandwidth requirements is increasing at a very rapid rate. But what we're observing is that the rates kind of vary based on the type of device and the workload. There are some devices like accelerators and workloads, right, that can benefit from more than even 2x bandwidth scaling that going to 120 gigatransfers provides, right? So we have been doubling bandwidth every generation on CXL, but there are workloads that can benefit from even more bandwidth increase. So one way to solve that is to be able to logically aggregate multiple CXL ports, and that's pretty much what the bundle port concept is. If you look at the memory expansion devices, right, they have been a bit ahead of the game because of the industry adoption and excitement. We already have such a model for memory expansion devices in the form of what we call MHSLDs. These are multi-headed single logical device that exists, and you can essentially connect. They have multiple heads, there is multiple ports, and you can connect them to a single host and thereby get sort of double the bandwidth of a single link. So that already existed, but what we did not have was a way to get the same multiplying effect for accelerators. So the bundle port concept, therefore, is sort of focusing on a type 1 and type 2 devices, and also type 3 accelerator devices, right? Not the expansion devices. These are the ones that operate using HTM-DV protocol for managing coherency. They don't use .cache, but .mem for everything. So this sort of addresses the challenge number 5, right? As you can see, so that there's number of heterogeneous workloads that we are seeing in the AI machine learning space and other areas that require higher bandwidth, and this is a way to address that in the CXL spec. Next slide, please. So let me talk a little bit about the bundle port construction, how devices are constructed, right? So if we look at the picture on the right, so you can see a CXL device that has basically 4 upstream ports, and those are divided into 2 bundles, what we call. The bundle 0 is the leftmost 2 ports, and the bundle 1 is made up of the right 2 ports. And if you look at the each of the bundle, there's one port that is a standard full capability CXL port, right, called SLD-B. It supports the full capabilities, as Debendra mentioned, fully backwards compatible, and that helps, right, with our promise that these devices will work in existing systems. The streamlined ports, that are the ones that are marked there, they are optimized for area and power. And the primary benefit that we get out of that is data bandwidth expansion at a lower cost. These are limited to 256 bytes flit mode only. So they can basically not support 68 byte flit mode. And also they optimize for UIO, unordered IO only. In theory, you could support the VC0 non-UIO, but that can be suboptimal. So by using these simplifications, these ports can essentially save area and power and can essentially just serve the need for data expansion. So because of the legacy port, right, SLD-B is shown here, legacy software can enumerate the bundle port device or BPD safely, and it can manage the individual ports, right? What it cannot do is take advantage of the bundling. Like what bundling does is allows the device to interleave traffic between different ports that are part of the bundle. If a device wants to snoop the host, it could use either of the ports, right, to issue the snoop within certain rules. For accessing the memory on the device, right, host can use either port, right? So that it's difficult to take advantage of those capabilities, right, performance enhancements without new software. We, however, recommend that these BPDs use different device ID to kind of make sure that they need new drivers for managing them. So accidentally, we don't want old drivers to start managing them because they won't understand what the second ports are doing. So, for example, why we need new software. So, one example is the new software would configure the IO memory instances above both the bundle ports so that all the ports will have the same view of memory. So where it helps is that you could have one port issue ATS request for getting translation to a GPA, and then use the host physical address returned by the ATS request on, let's say, port 0 on the other port, right? It could issue a .cache request on the SLD-B port and use HPA that was obtained from other port. So having the same consistent view for each ports is important, and that requires software changes. Next slide, please. This is sort of showing more topologies, how we can use bundled ports. Obviously, each topology comes up with the restrictions. So, but there are system constructs where these can be helpful. So the simplest one is with a switch is the one shown on the right, where we just have simple one-to-one port mapping. So the switch has 4 upstream ports, 4 downstream ports, and they are used to connect 2 devices. Each of them has a single bundle, right? So device A bundle 0 and device B bundle 0. So, and the traffic just flows straight up, right? There is no crisscross happening there. So that's the simplest one, right? On the left-hand side, it shows a CXL bundle device that has 2 ports connected directly to host and one other port connected to a switch. That is a supported construct for the spec. It will impose some limitations on how memory can be interleaved, etc., etc. But again, those are system-level decisions, right? That can be done based on the workload and the use cases that are being looked at. Right? So I'm going to next slide, please. Again, more switch topologies. So the left one shows that the streamlined port, in this case, both of them have a dedicated path. If you look at the SLD-B instances, the S, the ones that are marked S, on both the devices, they have a straight path going to the host to the switch. However, the legacy ones, the both of them go to a single USB on the switch, right? So switch has 3 upstream ports, 4 downstream ports, and there's they're connected right in this manner. You could also do uh, other pictures where the paths are merged, either right either on the one on the middle or one on the right. So again, they're just variations of different topologies that are possible. The exact topology would depend upon what the use case and the workload is. Again, lots of flexibility introduced by, and you can use it the way the system requires. Next slide, please. A few more things on the bundle port, right? So we wanted to keep things as simple as possible and keep the ports as independent as possible from functionality perspective. So for PM and reset purposes, each port in the bundle essentially acts on its own. So each port will return its own CDAT or the coherency table about memory map, etc., etc. The total capacity of BLD would be sum of all of its ports, right, together. So if you have, let's say, a device BLD with 2 ports, port 1 returns capacity of 20 gigabytes, other one reports 20 gigabytes, the total would be 40 gigabytes, right, of the BLD. Each of the BLD link will support the PM VDM exchanges as normal. They don't really have to interact with each other. They may also support GPF messages if appropriate. Each link can essentially observe hot resets on its own and can go through a reset on its own independently, right? Obviously, the software needs to take care of coordination, right? And that can be handled through the new device driver we talked about, right? There are some things that it doesn't make sense to have it on per port basis because those are basically device properties, right? An example is CXL reset, right? Or the disabling of the cache, right? So these are implemented as global controls that on either port, any port, but they affect the entire BLD. Right? The same thing with the TSP as well as IDE controls, right? So it doesn't really make a lot of sense to have IDE set up separately on the 2 ports, right? So they are essentially controlled to a single port and coordinated that way. Next slide, please. Okay, I think Debendra mentioned this, right? So we're seeing a lot of excitement around memory expansion devices, and there have been many deployments of memory expansion devices in the ecosystem, right? So as different members started deploying memory devices, they discovered some of the enhancement that were needed to make those successful, right? And many of those are essentially taking into account the learnings that they had as part of the early deployments. So I'll quickly go over this. So there were enhancements to improve corrected management around petrol scrubs. There was a couple of enhancements that allowed the OS or software to request platform to perform some of the RAS operations like post-package repair, right, or sparing on next boot, so that that provides more flexibility, right? Some of the operations like the hard PPR cannot be done dynamically in most devices or in the DDR. So this gives an OS an option to initiate hard PPR on a DDR device that's behind CXL Type 3 expansion. Next slide, please. This is sort of summarizing the how CXL spec has been moving along, right? So in the interest of time, I will skip this slide, but you can see the CXL bundle port and memory enhancement that were 2 things that are added at CXL 4.0 and this new speed. Again, Debendra has covered this really well. I think we have been sort of starting from CXL 1.1, which is single node. We're moving to multiple nodes in 2.0. a large fabric for 3.0 that has leaf and spine switches. And with 4.0, we have bundled ports and 120 gigabit transfers per second for higher bandwidth, right? So that has been, we've been consistently raising the bar every generation of CXL. Next slide, please. And again, this is really showing where we are in terms of the progress, right? So we have 280 plus members, right, that are active and participating in the consortium. One way to measure the where the deployments of products are is to look at compliance, right? So we had 9 compliance events in 2023, and lots of products have been brought into there uh, for uh, for uh, for compliance, right? So the last one was held just over a month ago, and at this point we have about 30 CXL 1.1 devices that are in the integrator list and 30 2.0 devices. And as we keep getting new and new devices and new vendors that want to participate, and that's really exciting, right? So, I mean, there's one part is to just develop the spec, but this is really where we see industry working and getting excited and finding new and new usages, right, that can benefit the ecosystem. Software development is in full swing. Linux kernel has been sort of leading the charter, and I think they started with the Type 3 device support, and now we are getting support for other features, right, as show up, right? Every release of Linux kernel is gaining new CXL features, as you can see. For the Type 1 and Type 2 devices, there are obviously deployments out there. There's primarily the benefit that folks are seeing is low latency and high throughput, right? That is difficult to see with some of the other technologies, right? So they're adopting that to get those benefits. Type 3, obviously getting lots of deployment. Primarily, I think this both of them are bandwidth expansion and capacity expansion are the main attraction. They're also seeing reduced latency that has been reported, and there's a link there that you can click on and have more details. There have been obviously multiple medias that are being placed on the Type 3 device. DRAM is obvious choice. We also have scenarios where folks are building storage, right, NAND type devices, right, on this Type 3 devices. Pooling is another exciting area that any discussion about CXL cannot really be complete without pooling. So there are many POCs that are happening, many promising results, several papers that are being published, and Debendra showed the picture and why people are excited about this, right? The amount of saving you can get from the saving DRAM cost is significant when you're considering a large data center. So there's also work happening on elastic memory demand, where workload can essentially change its requirements for memory pretty radically and very quickly. And we have capabilities in the CXL spec that allow this to change pretty quickly, right? So there's a paper that again you can follow the link later. Sharing in Fabric, it's also pretty exciting from a software development perspective, but it is lots and lots of new work, right? So there's silicon development happening. There's several software enabling work that's happening. Again, this has a lot of promise, but obviously it's a pretty radical concept, and it's will take time to get established, but it has a lot of promise. Next slide, please. Again, just to summarize, CXL 4.0 has yet again increased the speed and bandwidth that of the link, so we can meet the demands of new workloads that today's data centers demand. Double the bandwidth to 120 gigabit transfers per second, and with zero added latency. Right, that's very critical. And we also have the new by 2 width, right, as Debendra mentioned, right? So that allows you to have more devices attached to the switch or to the host at a by 2. We introduced bundled port, and I talked about that. We have driven number of memory enhancements in the RAS area. And while doing that, we have maintained compatibility with CXL 3.x, 2.0, 1.1, and even 1.0. So that your investments in those technologies can continue to be to pay back. And obviously, we are actually working in different working groups in the consortium to push the technology forward. I would encourage folks to come and join us. If you have new use cases that you're running into as you deploy CXL in your data center or with your customers, and you're running into challenges, right? Please bring those learnings to us, and we'll be happy to collaborate and move this technology forward. All right. So now we're in the question session.
Yes, thank you, Debendra and Mahesh. We will now begin the Q&A portion of the webinar. If you have any questions, please share those questions in the Q&A chat box. I can start with this first question, which is a three-part question regarding the FLIT layout. So can you explain the differences between the standard FLIT layout versus the latency optimized FLIT layout? When would you choose one versus the other? And how does interoperability work where there are two formats?
Okay. Next question for me. Can we go to that slide? I believe it was slide 15. Yeah, I think the next one. Yes. Okay. So can you repeat the question again?
It was
Let's do
explain the
one at a time.
differences between the standard FLIT layout
Oh,
versus the latency optimized FLIT layout.
standard versus the latency. Okay. So, you can see that fundamentally the standard one has got 8 bytes of CRC and 6 bytes of FEC. The latency optimized one has got 6 bytes of FEC, but the CRC assignment is different and how we treat them is different. Of course, you can see that there are 2 6 bytes of CRC, so there are 4 more total bytes of CRC on the latency optimized one. But the basic thing we are trying to do here is, with the standard FLIT layout, you are going to get the FLIT, you are going to apply the FEC, and then you're going to do the CRC check. If things pass, great. If they don't pass, then what happens is you go back and ask for the FLIT again. Now, in the latency optimized one, you are going to first check the CRC. You're going to get 128 bytes, the even FLIT half. You're going to check the CRC. If it passes, that's it. That's gone. That's consumed. And then you're going to get the next one, and you're going to check the CRC first. If it passes, it's gone. If it fails, then what happens is you then go back and apply the FEC across the 3 FEC groups, across the entire 256 bytes, and then apply CRC. If it fails, then you're going to ask for a replay. Now, the question is, hey, I got something where the even FLIT half passed, but the odd had a problem and I had to do a replay. What happens? Well, we will remember that we have consumed the even half. So even if we replay the entire FLIT, we are going to ignore the even FLIT half when it gets replayed, and we are just going to do the odd FLIT half. So that's basically the difference. It's, as a result, what is happening is you're basically gaining the 128 bytes in case there is no error, that much of latency. What is the second part?
When would you choose one versus the other?
When would you choose one versus the other? And the other one was how does backward compatibility work? Okay. So if latency is of critical concern, you would choose, and of course, assuming which kind is related to the next one. So think of it as the standard. The name is standard. It means that everybody needs to do it. Okay. Now, if two components end up doing latency optimized, that means they are sensitive to the latency. So you're going to choose the latency optimized, right? So latency optimized is the additional one. It's an optional feature. So both sides need to have latency optimized so that becomes what they use in that link. And the way backwards compatibility work is everybody has to do the standard FLIT layout. So next question.
Right. In the same vein of interoperability, how does that work with prior generation such as CXL 1 and 2, which have a 68 byte FLIT mode?
68 byte FLIT mode, yes. So if you are doing CXL 3.0 or 4.0 for that matter, you must be implementing the CXL 1.0, 1.1, and 2.0, with the exception of the bundle link, the non-compliant part, right? But even in the bundle link, there is one link where you have to be fully backwards compatible. So that's how you are going to interoperate there.
And there's questions regarding the bundled port. So does the second port in a bundle have to be a streamlined port, or can it be a regular port?
So let me take that one. Yeah, it can be a regular port. There's no restriction on that. However, implementing a streamlined port obviously allows you to have better area and power, right? Uh, Characteristics of your device. Right? So, but yeah, both options are possible.
All right, and another one here is, what do you mean by a Type 3 accelerator devices? I thought Type 3 devices are for memory expansion.
Yeah, I mean that's actually a common question, right? So when we started CXL 1.1, I think Debendra showed a picture. I don't know if you can go back to that one. Um, it's all the way back in, yeah, that one, yeah. So if you look at this, the Type 3 devices were used as memory buffer expansion back in 1.1, even 2.0 timeframe. In later, we added ability to maintain coherency using CXL.mem. We call it HDM-DB or device managed coherency using backend validate. And that effectively allows the Type 3 device to manage coherency with the CPU host and thereby perform accelerator functionality. So now we have two subtypes of Type 3 devices. One that are classic memory buffers that just respond that appear as memory expansion devices that just have memory. And then we have Type 3 accelerators, which they have memory, but in addition, they can also perform computation along with the CPU and manage cache coherency. I hope that answered the question.
Perfect. I know we're coming up to the time here, so maybe we can address one more question before we close out the webinar for today. This one's a little bit more of a forward-looking question. So where does CXL go after CXL 4.0?
Yeah, so let me take that one. So clearly, it's a journey. It's a multi-decade journey. These technologies are being widely deployed. So, you can expect to see, we generally don't comment on things that we are working on, but some things that you can pretty much expect to see us do, which is, of course, more speeds and feeds. And then, of course, additional usage models and learnings as we gather from the deployment, we are going to, of course, incorporate them. We are in it for the long haul, right? I mean, these technologies have, as I said, multi-decade lifespan, and that's what we were going to work towards. And what I would say is that stay tuned, get involved in the work groups, of course. Then then you have a say in terms of how the technology evolves. That's where I'll leave it at.
All right, well, I think that leads us to the conclusion of our webinar. Thank you, Debendra and Mahesh, for sharing your expertise. We will address all the questions that we weren't able to cover today in a future blog, so please follow the CXL Consortium on LinkedIn for those updates. The presentation recording will be available on our YouTube channel, and we'll also upload our slides to the CXL Consortium website. But thank you so much for attending the CXL 4.0 specification webinar.
Right.
Thank you, everyone.
Thank you.